Alright, hi everyone. My name is Taofiq from Spiral Blue. We are an Earth observation company, but the way that we are trying to make Earth observation more accessible, more affordable, essentially democratizing it, is actually by putting computers on EO satellites, similar to Tony's work, which we do look forward to working with ourselves. But a bit of background on us. There's a reason we're working on Earth observation. Like many of us, my background is aerospace engineering. Wanted to do that because I got into astronomy as a kid. But of course, you cannot look at settling other planets unless you look after the Earth first. So hence Earth observation. A bit on the team. It's not just myself. I've got a pretty solid founding team at the moment. Should be destroying my audio systems. Alright, not move my hand again. So yeah, in addition to myself, we've got my CTO, James Buttonshaw. Got a lot of experience with defence and government contracting with companies such as BAE and Nova, who I note is in attendance today as well. And our head of AI, Dr. Henry Zong, pushing the boundaries of science, quite literally, in the area of machine learning and artificial intelligence. And not just any ML and AI, because that's a very common thing that I think a lot of people say that they do nowadays, but very lightweight machine learning and artificial intelligence. Very necessary to actually put such processing algorithms on very low swap environments in space. So in terms of the problems that we're solving, in Earth observation, a key problem that we do see is satellites are quite limited in terms of how much bandwidth they do actually have to send data down. So the usual numbers are between 1 to 5%. So a satellite could be going around the Earth for capturing 6 million square kilometers per day, but only be able to send down, well, we've seen a case where the satellite was only able to send down 300,000 square kilometers per day. And considering satellites make dollars on a per square kilometer basis, that's a lot of money that they're potentially leaving on the table. So that's something we'd like to help with. But because of this, there's problems with accessibility, there's problems with the pricing models. For example, this is something I've personally been dealing with, trying to sell satellite images to a client. It's still ongoing, and it's taken over 2 months so far, and that is an order size of $2,000. Right? Imagine you go to Office Works and you're trying to buy a laptop, and it takes them 2 months to reply to you, and then you're like, oh, what kind of laptop would you like? And what would you like the laptop to do? And you tell them, and then it takes another, and then at the end of 2 months, you still haven't got it. That's the situation right now with satellite imagery. In addition to that as well, the other part is minimum order quantities. To order satellite imagery, you have to hit a certain minimum level of spend. It could be $1,000, it could be $5,000. And that's because when a satellite captures an image, it can't sell part of the image. It has to sell the whole image. So one of our case studies with one of our clients is actually, in the past, a farm needed to capture imagery for about 60,000 hectares of farmland. And that's a reasonably sized farmland, right? But because it was spread out across multiple fields, they actually had to capture satellite imagery of each field separately. So they actually had to order 1 million hectares of imagery to actually capture 60,000. Literally paying 17 times more than what they needed to, which they did for some reason, don't ask me why. But yeah. And the other thing, of course, is in Earth observation, you're dealing with huge quantities of data, even when you do get it back. And you don't necessarily want to do that. You want to have an answer, you want to have an insight. And I'm not saying this as a purely hypothetical basis. We had a customer say this to us unprompted a couple of weeks ago. And that's very exciting because that customer is paying us a lot of money. So we'll see how we go with that customer. So it's, yeah, the classic example here, of course, is imagine if you had to get all the weather data, satellite imagery data, weather station data, in order to make yourself a weather report. And in order to have done that, you have to have all the processing systems, all the infrastructure, software, and meteorology degree to get a weather report. No one would get that. So what we're doing, in bringing these two problems together, one thing that immediately pops out is, well, what if you could process this data in space, right? So our solution to that is what we call the space edge computer. But more broadly to that is we're not just we're not a closed ecosystem. We're looking to work with many different partners, many different companies to build an ecosystem where someone can actually come onto our platform, task a satellite, ask it to do a specific piece of analysis on whatever area of interest that they're after, and then get it done, either through our satellites, through satellites carrying our hardware, through satellites carrying AI craft hardware, or really whatever system is even appropriate. We could even have customers coming in that don't even know that edge computing is happening. That's the level that we need to reach. But for now, to get this going, in space, the biggest uncertainty is can we actually get this stuff working? So of course, we're building space edge computers. This is our Space Edge 0 model. We've got a more up-to-date Space Edge 1 model as well, which is about 20 times more powerful. This stuff moves forward pretty fast. And that Space Edge 1 is what we'll be flying on board Waratah C. And the cool thing is, in terms of specs, which I don't have on here unfortunately, but I'm happy to share the spec sheet with everyone. In terms of specs, we are achieving about 10 to 20 teraops per second of processing power. And that, I say it's a range because it depends how you measure it, and it's not standardized, which annoys me, but that's how it is, unfortunately. And our average in-orbit power use is 6 watts when we're doing heavy processing loads. However, it does spike up quite considerably to as high as 20 watts. So we have actually been looking at ways to clamp that down, especially for Waratah C, where it is a very power-constrained platform. And so far, we've been able to bring that down to about 8 watts, which I think is the limit. So, and as far as we're doing, we're still doing the tests, but we may not lose too much in the way of processing power in bringing that power usage down. So obviously we'll see what the actual results are. So obviously this is a Cubesat model, but we're also going to be flying later this year on a small satellite, a Satellogic 50 kilogram NewSat, I believe that they call those. That will actually carry a 1 meter resolution Earth observation camera. So we will be able to actually do a full end-to-end test of having a customer order imagery, and then ultimately get back a piece of analytics or a piece of insights that they actually need. In terms of how it works, this is the model I just explained. We actually have this operating now for that customer that I was mentioning earlier. But the graphics have changed a little bit. Hopefully the next time I present this, we will have updated that. But yeah, it's running. We're getting it improved over time so that the customer will be able to not just task imagery, but also task, for example, forest canopy cover, risk or areas at risk of erosion, areas that are hard areas, so that you can know inside a local government area what areas you need to, essentially figure out your flood model, right? This sort of stuff. These are the answers that a lot of, especially government customers are looking for. So that's what would ultimately be delivered on the other side. Of course, ship detection is a classic use case, hence that's what's on their own program. In terms of our technology, I've already spoken a little bit on the hardware. Obviously, we're looking at getting software and hardware protection, software and hardware-based shielding for the computers. The way exactly we're doing it, I can't tell you because obvious reasons, right? But that's what we're looking at. Obviously, we're looking at as well thermal, I guess not so much shielding, but more efficiently being able to carry away heat from the device to the structure of the satellite, from where it can be emitted out into space. And if anyone has smarter ways of doing that than what we have, I would be very keen to talk. I think we're already talking to UTS about that, but yeah, keen to get smart ways to do that. Also, on the shielding side of things, if anyone has a way to shield a satellite being hit by microwave beams, I would be very interested. I will say, and the reason I say this is because the Russians are shooting microwave beams at satellites to try to knock them out. So it's very topical right now. In the middle, we have our middleware layer, as you may call it. And what that allows us to do is to run not only our software applications essentially as microservices on board our hardware, but potentially other companies as well. And so in fact, we are actually planning to have a hackathon later this year in October alongside the NASA Space Apps Challenge, where we're inviting a whole bunch of students, professionals, essentially whoever's interested to come in, try accessing our hardware, try writing some software that could actually process some imagery or some other data on satellite for whatever application, whether it be for Earth observation, whether it be for robotics or autonomy, whatever it is. And then the winning team will obviously get a bit of cash from us, but the other finalists will actually get the opportunity to test their code in space as soon as we can. So looking forward to, I guess we have made that, I think we're about to make that announcement formally, but it's we need to get that out there to try and get as many people interested as possible. Because really, we do see that while we have our own sort of machine learning algorithms, for specific use cases where we're not necessarily interested, we want others to come in and really build that ecosystem. So that's what we're looking to do. But on our machine learning side, I can say that our machine learning models are about 50 times smaller than the state of the art. So that is the difference between uploading a new machine learning model in response to some changing condition in a day versus 2 months. Right? So that's what we're doing on that front. And oh yeah, in terms of accuracy, it's getting to near human levels of accuracy. Turns out humans are only about 95% accurate in actually classifying things, and we're about 94%, so we're getting there. So yeah, that's us. Hopefully that didn't take too long and we can all get to beers nice and quick. Unfortunately I can't stick around for too long afterwards, but I might leave some cards on the table if anyone wants to get in touch. Obviously there's a lot of stuff happening with space in Australia at the moment, and we can work together. So thank you very much.